A high school student just changed everything we thought we knew about one of the most important discoveries in modern astronomy. Not a professor. Not a veteran researcher. A student reviewing data that thousands of scientists had already seen. In January 2020, NASA announced something extraordinary. TESS, the Transiting Exoplanet Survey Satellite, had found an Earth-sized world sitting in the habitable zone of a distant star. TOI-700d. The first discovery of its kind for this particular spacecraft. A planet where liquid water could theoretically exist on the surface. But here's what makes this story remarkable. The discovery almost didn't happen. Because the star itself was wrong. Let me explain what that means. TOI-700 sits 101.4 light-years away in the constellation Dorado. To put that distance in perspective, the light reaching our telescopes today left that star in the early 1920s, around the time archaeologists were unsealing King Tutankhamun's tomb. When TESS first catalogued this star, scientists classified it as something similar to our Sun. Bigger, hotter, brighter. Which meant the planets orbiting it appeared larger and hotter than they actually were. The outermost planet looked too big, too scorched, too hostile for life. Then Alton Spencer noticed something off in the data. Spencer, working with the TESS team, caught an inconsistency. The stellar parameters didn't match. When researchers recalculated the star's true properties, everything shifted. TOI-700 wasn't Sun-like at all. It was a red dwarf, about 40% the mass and radius of our Sun, running at roughly half the temperature. Suddenly, the planets shrank. Their temperatures dropped. And the outermost world, TOI-700d, transformed from an inhospitable rock into something far more intriguing. Emily Gilbert, a graduate student at the University of Chicago leading the research team, put it simply. When we corrected the star's parameters, the sizes of its planets dropped, and we realized the outermost one was about the size of Earth and in the habitable zone. That correction changed everything. But what exactly is TOI-700d? What makes this planet special enough to warrant NASA's attention and the deployment of some of the most sophisticated instruments humanity has ever built? Start with the basics. TOI-700d is roughly 1.19 times the radius of Earth. Slightly larger, but not dramatically so. It completes one orbit around its star every 37.4 days. A year on this world lasts about as long as a single month here. The planet sits 0.161 astronomical units from its host star. That's much closer than Mercury's orbit around our Sun, which clocks in at 39 cents. Under normal circumstances, being that close to a star would turn a planet into a charred wasteland. Except TOI-700 isn't a normal star. Red dwarfs dominate our galaxy. They make up somewhere between 70 and 80% of all stars in the Milky Way. Small, cool, dim, and incredibly long-lived. These stars burn their fuel so slowly they can survive for trillions of years. Our Sun will die in about 5 billion years. Red dwarfs. They'll still be shining long after the last Sun-like star has gone dark. TOI-700 runs cooler than our Sun by a significant margin. That closer orbital distance doesn't mean TOI-700d is getting roasted. In fact, the planet receives about 88% of the energy Earth gets from the Sun. Not identical, but remarkably similar. Enough to potentially support liquid water if the right atmospheric conditions exist. Here's where it gets interesting. The planet is dense. Really dense. Recent observations using the espresso spectrograph on the Very Large Telescope measured TOI-700D's mass at about 2.4 times Earth's mass. Combined with its slightly larger radius, that gives the planet a bulk density of roughly 8.5 grams per cubic centimeter. Earth's average density sits around 5.5 grams per cubic centimeter. What does that density tell us? The planet is likely dominated by rocky and metallic materials, possibly with a larger iron core relative to its size compared to Earth. This isn't a puffy gas giant or an icy world. TOI-700D is solid, heavy, and structured more like our home planet than many worlds we've discovered. The habitable zone designation matters here. Scientists sometimes call it the Goldilocks zone, the region around a star where temperatures are neither too hot nor too cold for liquid water to exist on a planet's surface. But that name is misleading. Being in the habitable zone doesn't guarantee habitability. It's a necessary condition, not a sufficient one. Venus sits in our Sun's habitable zone. Its surface temperature reaches 465 degrees Celsius, hot enough to melt lead, thanks to a runaway greenhouse effect. Mars technically grazes the outer edge of the habitable zone, yet its surface is a frozen desert with an atmosphere so thin it might as well not exist. Location matters, but so does atmosphere, magnetic field, geological activity, and stellar radiation history. TOI-700D has advantages many red dwarf planets lack. Its host star is remarkably calm. Over 11 observation sectors, tests detected 0 white light flares from TOI-700. That's unusual. Red dwarfs are notorious for violent stellar flares, massive bursts of radiation that can strip away planetary atmospheres and sterilize surfaces. The fact that TOI-700 shows such low activity makes its planet significantly better candidates for detailed habitability studies. The star's low rotation rate reinforces this. Slow rotation typically indicates low magnetic activity, which means fewer flares, less extreme radiation, and a more stable environment for any planets in the system. This quiescent nature gives TOI-700D something many exoplanets orbiting red dwarfs don't have: time. Time for an atmosphere to form and stabilize. Time for complex chemistry to develop. Time for conditions to settle into something resembling equilibrium. Scientists estimate that a planet with Earth-like atmospheric pressure could retain its atmosphere around TOI-700 for longer than 1 billion years. That's a geological timescale. Enough time for significant evolutionary processes to occur, if life ever took hold. The discovery process itself reveals how far exoplanet science has come. TESS doesn't work like its predecessor, Kepler. Kepler stared at a single patch of sky for years, monitoring about 150,000 stars continuously. TESS scans nearly the entire sky, focusing on the brightest, nearest stars. It divides the sky into sectors, each covering a 24 by 96 degree area, and observes each sector for 27 days. TOI-700 appeared in 11 of the 13 sectors TESS observed during its first year. That extended coverage was crucial. The planet's 37-day orbital period meant scientists needed multiple observation windows to catch enough transits to confirm the discovery. A transit occurs when a planet passes in front of its star from our perspective, causing a tiny dip in the star's brightness. For Earth-sized planets around distant stars, these dips are minuscule. Detecting them requires incredible precision and repeated observations. TESS caught the transits. But confirmation required another instrument. NASA's Spitzer Space Telescope, nearing the end of its mission in January 2020, provided the final verification. Spitzer's infrared observations sharpened the measurements of TOI-700D's orbital period by 56% and its size by 38%. More importantly, Spitzer ruled out false positives, scenarios where something other than a planet could produce a similar signal in the data. False positives plague exoplanet detection. A smaller, dimmer companion star in the system could mimic a planetary transit. So could certain types of stellar activity or instrumental artifacts. Independent confirmation from multiple instruments isn't just good practice, it's essential. Spitzer's data transformed TOI-700D from a candidate into a confirmed planet. The TOI-700 system doesn't stop at planet D. 3 other confirmed worlds orbit the star, each offering its own scientific insights. TOI-700b, the innermost planet, is almost exactly Earth-sized and probably rocky. It completes an orbit every 10 days, sitting too close to the star for liquid water but providing valuable data on how rocky planets behave under intense stellar radiation. TOI-700c, the middle planet, measures 2.6 times larger than Earth. It orbits every 16 days and likely has a thick gaseous envelope, placing it in the category between rocky worlds and ice giants that scientists call subneptunes. This planet helps researchers understand the transition point where planets stop being rocky and start accumulating thick atmospheres of hydrogen and helium. Then there's Planet E, discovered in 2023 after TESS observed the system for another year. TOI-700e is 95% the size of Earth and orbits every 27.8 days, placing it at the inner edge of the habitable zone between planets C and D. With the confirmation of Planet E, TOI-700 became one of only a handful of known systems with 2 Earth-sized planets orbiting in the habitable zone of their star. Astronomers call systems like this keystones. They're rare, valuable, and scientifically crucial. Having 2 potentially habitable worlds in the same system allows for comparative exoplanetology, studying how different conditions within the same stellar environment affect planetary characteristics. It's like having a controlled experiment on a cosmic scale. But here's what we don't know yet. What TOI-700d actually looks like. Scientists have never seen the surface of TOI-700d. They've never analyzed its atmosphere. They don't know if it has oceans or continents or ice caps. What they do have is data. Numbers. Measurements. And from those measurements, they've constructed models. 20 different versions of what this world might be. One scenario pictures TOI-700d as an ocean world. Liquid water covering the entire surface, kilometers deep. The atmosphere in this model is thick with carbon dioxide, similar to what Mars may have looked like billions of years ago when it still had flowing water. Dense clouds blanket the star-facing hemisphere, reflecting light back into space and moderating temperatures. This isn't just speculation. Early Mars had rivers, lakes, possibly even an ocean in its northern lowlands. Evidence is written in the rocks. If TOI-700d follows a similar path, it could be a water world with a carbon-rich atmosphere capable of sustaining a stable climate. Another model goes in the opposite direction. A dry, cloudless planet with no oceans at all. Just exposed rock and perhaps ice at the poles. Winds race across the surface, driven by the temperature difference between the perpetual day side and eternal night. On this version of TOI-700d, air flows away from the frozen night hemisphere, converging at the point directly beneath the star where temperatures peak. Between these extremes lie countless other possibilities. A planet with shallow seas and exposed continents. A world locked in a permanent ice age with liquid water only in equatorial regions. A Venus-like hellscape where a runaway greenhouse effect has boiled away any chance of habitability. Each model is scientifically plausible given what we know about the planet's size, mass, and the energy it receives from its star. The problem is we can't distinguish between them yet. Not with current technology. The light from TOI-700d is drowned out by its star. The planet is too small, too far, too faint for direct observation. What we need is spectroscopy. When starlight passes through a planet's atmosphere during a transit, molecules in that atmosphere absorb specific wavelengths of light. By analyzing which wavelengths are missing, scientists can determine the atmospheric composition. Water vapor, oxygen, methane, carbon dioxide. Each leaves a unique fingerprint. But TOI-700d's atmosphere, if it has one, produces a signal too weak for current instruments to detect reliably. The James Webb Space Telescope is the most powerful observatory ever built, but even it struggles with Earth-sized planets around red dwarfs. The challenge isn't just distance. It's the star itself. Red dwarfs are unpredictable. Most of them anyway. They flare. They erupt. They emit bursts of radiation that can fry planetary atmospheres and sterilize surfaces. TOI-700 is different. Over the 11 sectors TESS observed, not a single white light flare was detected. The star's rotation rate is slow, another indicator of low activity. This matters enormously. Think about it this way. If you're trying to build a habitable world, you don't want the star constantly bombarding it with high-energy radiation. Flares can strip away atmospheres. They can damage biological molecules. They make the surface a hostile place for complex chemistry. TOI-700's quiet nature is one of the strongest arguments for its planets being potentially habitable. The star isn't trying to destroy them. This stability extends to the solar wind, the stream of charged particles flowing out from the star. Models suggest that TOI-700d experiences solar wind pressure similar to what Earth receives from the Sun. That's critical for atmospheric retention. A planet's magnetic field can deflect the solar wind, creating a protective bubble. Earth's magnetosphere shields us. Mars lost its magnetic field billions of years ago and its atmosphere was slowly stripped away. If TOI-700d has a magnetic field, it could maintain an atmosphere over geological timescales. Evidence from the inner planet supports this. TOI-700c, the sub-Neptune orbiting between planets B and D, has retained a thick hydrogen and helium envelope. If the star's radiation was intense enough to strip that away, it would have done so by now. The fact that planet C still has its atmosphere suggests the star's high-energy emission is insufficient to cause significant atmospheric loss. TOI-700d, receiving less than half the radiation that planet C does, would be even less vulnerable to photoevaporation. The planet's density adds another layer to the puzzle. At 8.5 grams per cubic centimeter, TOI-700d is significantly denser than Earth's 5.5. That suggests a composition dominated by heavy elements. A large iron core. Rocky mantle. Possibly a thin atmosphere compared to the thick gaseous envelope you'd expect on a planet with lower density. These measurements came from radial velocity observations using the espresso spectrograph on the Very Large Telescope in 2024. The technique is precise. As a planet orbits its star, the gravitational pull causes the star to wobble ever so slightly. By measuring the star's motion, scientists can calculate the planet's mass. Combined with the radius from transit observations, density falls out of the math. TOI-700d's high density is consistent with a rocky planet, potentially with a thin secondary atmosphere rich in heavier molecules like nitrogen and carbon dioxide rather than hydrogen and helium. But density alone doesn't tell you about habitability. You need to know the temperature. The equilibrium temperature, the theoretical temperature assuming no atmosphere, is about -4 degrees Celsius. Just below freezing. That's cold, but not impossibly so. If the planet has an atmosphere with greenhouse gases, the surface could be significantly warmer. Earth's atmosphere raises our surface temperature by about 33 degrees Celsius compared to what it would be without greenhouse warming. A similar effect on TOI-700d could push temperatures well into the habitable range. However, there's a risk. Too much greenhouse warming leads to a runaway effect. Venus experienced this. Its thick carbon dioxide atmosphere creates surface temperatures hot enough to melt lead. On TOI-700d, the possibility of a runaway greenhouse exists, though models suggest it's unlikely. The planet receives 88% of the energy Earth does from the Sun. That's enough to warm the surface, but probably not enough to trigger a complete atmospheric collapse into a Venus scenario. Probably. The word probably appears a lot in discussions of TOI-700d. Scientists deal in probabilities, not certainties. The models are educated guesses based on the best available data. They're useful for guiding future observations, for identifying which questions to ask next. But they're not answers. What would actually confirm habitability? Biosignatures. Evidence of life in the atmosphere. On Earth, oxygen is a biosignature. It's produced by photosynthetic organisms and reacts quickly with other molecules, so it doesn't persist in the atmosphere without constant replenishment. If you detected oxygen in the atmosphere of an exoplanet, especially alongside other gases like methane that shouldn't coexist in equilibrium, that would be strong evidence for biological activity. TOI-700d is unlikely to show such clear biosignatures even if life exists there. The planet is tidally locked. One hemisphere always faces the star, the other always faces away. This creates extreme temperature gradients unless the atmosphere is thick enough to redistribute heat. On a tidally locked world, you might not get the kind of global biosphere Earth has. Life, if it exists, might be confined to a narrow band around the terminator, the boundary between day and night, where temperatures remain moderate. Or perhaps life thrives in the oceans beneath a frozen surface on the night side. Or in the clouds on the day side. Or nowhere at all. The planet might be completely sterile. A lifeless rock orbiting a quiet star in the constellation Dorado, 101 light-years from Earth. The distance is worth considering. 101 light-years sounds vast, and it is by human standards. But in astronomical terms, it's remarkably close. The light we see from TOI-700 today left the star in the early 1920s, around the time archaeologists discovered King Tutankhamun's tomb. That's recent history. It means this system is accessible for detailed study in ways that more distant exoplanets aren't. Future telescopes will observe TOI-700d. They'll attempt to detect its atmosphere, measure its composition, search for signs of water vapor or other molecules that might indicate habitability. These observations will take years. Decades possibly. The answers won't come quickly. But the fact that we can ask these questions at all, that we can identify potentially habitable worlds in nearby star systems and begin characterizing them, represents a profound shift in human knowledge. For most of history, we didn't know if planets existed beyond our solar system. Now we're debating whether specific distant worlds might host life. TOI-700d exists at the intersection of what we know and what we hope to discover. It's a world defined by its potential, by what it might be rather than what we can prove it is. And that uncertainty is precisely what makes it fascinating. The discovery itself was almost accidental. TOI-700d was hiding in plain sight, buried in data that had been misinterpreted from the start. TESS, the Transiting Exoplanet Survey Satellite, captured the signal. A tiny dip in starlight, repeating every 37.4 days. The automated systems flagged it as interesting, added it to the catalog, and moved on. But the initial classification was wrong. The star TOI-700 was labeled as more massive and hotter than it actually is. That error cascaded through every calculation. The planets appeared larger, hotter, less interesting. TOI-700d looked like a scorched world, too hot for water, too hostile for serious consideration. It sat in the database for months, unremarkable, overlooked. Then a high school student noticed something odd. Alton Spencer, working with members of the TESS team, cross-referenced the stellar parameters with other databases. The numbers didn't match. He flagged the discrepancy. Scientists double-checked. The star was smaller, cooler, quieter than the catalog claimed. When they recalculated the planet's properties using the corrected stellar parameters, everything changed. TOI-700d shrank. Its temperature dropped. It moved from the category of too hot to matter into the habitable zone. The planet that had seemed irrelevant suddenly became one of the most important discoveries in the TESS mission. Emily Gilbert, a graduate student at the University of Chicago, led the team that confirmed the finding. She later described the moment of realization. They corrected the star's parameters, the sizes of the planets dropped, and they realized the outermost one was about the size of Earth and in the habitable zone. It's a reminder that scientific discovery isn't always dramatic. Sometimes it's just careful checking. Sometimes a high school student catches what professionals missed. Sometimes the most exciting finds hide behind simple mistakes. TESS observed TOI-700 for an unusually long time. The star appeared in 11 of the 13 sectors monitored during the mission's first year. That's fortunate. Most stars get 27 days of observation, a single sector. TOI-700 got nearly a year. The extended coverage allowed scientists to catch multiple transits of all 3 planets then known in the system. Each transit provided data. Each data point refined the measurements. The transit method is elegant. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light. The amount of dimming reveals the planet's size. The timing between transits reveals its orbital period. String enough transits together and you can calculate the orbit's shape, the planet's distance from the star, even estimate its temperature. For TOI-700d, the signal was faint. The planet is only about 20% larger than Earth. Its transit blocks roughly 0.04% of the star's light. That's barely detectable even with sensitive instruments. Background noise, stellar variations, instrumental errors, all of these can mimic or obscure a transit signal. That's why confirmation matters. NASA's Spitzer Space Telescope provided that confirmation. Spitzer was nearing the end of its mission in early 2020, scheduled to shut down in January. But before it did, scientists pointed it at TOI-700. Spitzer observed in infrared wavelengths, different from TESS's visible light observations. The infrared data confirmed the planet's existence, refined its orbital period by 56%, and sharpened its size measurement by 38%. More importantly, Spitzer ruled out false positives. The signal wasn't a background star, wasn't instrumental noise, wasn't a smaller, dimmer companion orbiting TOI-700. It was a planet. TOI-700d became the first Earth-sized planet in the habitable zone discovered by TESS. That designation carries weight. TESS launched in April 2018 with a specific mission: survey the nearest and brightest stars, find planets around them, identify candidates for detailed follow-up by more powerful telescopes. By January 2020, TESS had found hundreds of planets. But TOI-700d was the first Earth-sized world in the habitable zone. The habitable zone concept is straightforward. It's the region around a star where surface temperatures could allow liquid water. Too close to the star and water boils away. Too far and it freezes solid. The zone's boundaries shift depending on the star's temperature and brightness. Around hot, bright stars like our Sun, the habitable zone sits farther out. Around cool, dim red dwarfs like TOI-700, it hugs close to the star. TOI-700d orbits at 0.161 astronomical units from its star. For comparison, Mercury orbits our Sun at 39 cents. TOI-700d is closer to its star than Mercury is to ours. But TOI-700 is roughly half the temperature of the Sun and about 40% its mass and radius. The planet receives 88% of the stellar energy Earth gets. That places it comfortably in the habitable zone, though probably toward the cooler end. The planet's mass presented a puzzle initially. Transit observations reveal size, not mass. Mass requires different methods. Radial velocity observations detect the gravitational tug a planet exerts on its star as it orbits. That tug causes the star to wobble slightly. The size of the wobble indicates the planet's mass. In 2024, astronomers used the espresso spectrograph on the Very Large Telescope to measure TOI-700d's mass. The result was surprising. 2.4 times Earth's mass, give or take about 0.5 Earth masses. That's heavy for a planet only 20% larger in radius. The bulk density calculation came out to roughly 8.5 grams per cubic centimeter. Earth's density is about 5.5 grams per cubic centimeter. What does that density mean? It suggests TOI-700d is predominantly rocky with a large iron core. Perhaps the core makes up a larger fraction of the planet's total mass than Earth's core does. Or perhaps the planet's internal pressures compress its rocky mantle more than Earth's mantle is compressed. Either way, the high density rules out substantial amounts of water or thick gaseous envelopes. This is a dense, rocky world. But density alone doesn't determine habitability. Atmosphere matters. Surface composition matters. Geological activity matters. Magnetic fields matter. TOI-700d could be a barren rock with no atmosphere, its surface scoured by stellar radiation. Or it could have retained a thick atmosphere, protected by a strong magnetic field, with active geology recycling materials and maintaining surface conditions suitable for liquid water. The star's behavior offers clues. TOI-700 is a red dwarf, spectral class N. Red dwarfs are the most common stars in the galaxy, making up 70 to 80% of all stars. They're small, cool, long-lived, and often temperamental. Many red dwarfs produce frequent powerful stellar flares, bursts of radiation that can strip away planetary atmospheres and sterilize surfaces. TOI-700 is different. Over 11 sectors of TESS observations, the star showed no white light flares. None. Its rotation rate is low, another indicator of minimal stellar activity. This quiescent nature is unusual for red dwarfs and critically important for habitability. A calm star gives its planets a chance to retain atmospheres over billions of years. Computer models suggest TOI-700d could maintain an atmosphere with Earth-like pressure for over 1 billion years. The solar wind pressure and magnetic field intensity are expected to be similar to what Earth experiences. That's encouraging. Atmospheric retention is one of the biggest challenges for planets around red dwarfs. The fact that TOI-700d likely experiences conditions similar to Earth's improves its odds. Scientists modeled 20 different potential environments for TOI-700d. These weren't predictions but explorations of possibility. What could the planet be like given its size, mass, orbital distance, and stellar characteristics? One simulation depicted an ocean-covered world with a thick carbon dioxide atmosphere, similar to what Mars might have had billions of years ago. Another showed a dry, cloudless planet where winds converge on the point directly facing the star. A third included deep cloud layers on the day side, reflecting starlight and moderating temperatures. Each model makes different assumptions about atmosphere, surface composition, rotation, and heat distribution. None can be confirmed without direct observations, but they provide targets. When future telescopes observe TOI-700d, scientists will compare the actual data to these models. Whichever model matches closest will reveal what the planet actually looks like. TOI-700d is tidally locked. That's almost certain given its proximity to the star and the age of the system. Tidal locking means one hemisphere always faces the star while the other remains in perpetual darkness. Earth's moon is tidally locked to Earth. We always see the same lunar face. For a planet, tidal locking creates extremes. The day side bakes under constant starlight. The night side freezes in endless darkness. Without an atmosphere, the temperature difference would be catastrophic. With a thick atmosphere, powerful winds could redistribute heat, creating a twilight zone around the terminator where temperatures remain moderate. Life, if it exists, might cluster there. Or perhaps beneath ice on the night side. Or floating in clouds on the day side. The possibilities multiply when you don't know the conditions. TOI-700 wasn't finished surprising astronomers. In November 2021, analysis of extended TESS observations revealed a fourth planet. TOI-700e, confirmed in January 2023, is 95% Earth size and orbits every 27.8 days. It sits between planets C and D, also within the habitable zone but closer to the inner edge. It receives about 30% more stellar flux than Earth does. The TOI-700 system now has 2 potentially habitable Earth-sized planets. That's extraordinary. It makes TOI-700 what astronomers call a keystone system. These are rare. Having multiple planets in the habitable zone of the same star allows comparative studies. How do similar worlds in slightly different conditions develop differently? Do both retain atmospheres? Does one become a water world while the other stays dry? Keystone systems aren't just interesting. They're transformative. When you have 2 planets in the habitable zone of the same star, you control for stellar variables. Same radiation output, same stellar wind, same magnetic field. The differences between the planets become clear. If one develops oceans and the other doesn't, you know it's not about the star. It's about the planet itself. mass, composition, geological activity, atmospheric chemistry. These systems let scientists isolate variables in ways single-planet systems never could. TOI-700 now sits among an elite group. Only a handful of known systems have multiple habitable zone planets. TRAPPIST-1 has 3. Kepler-62 has 2. Each one offers a natural laboratory for understanding how worlds evolve under similar stellar conditions but different planetary circumstances. The value compounds over time as observation technology improves. Think about what astronomers can learn. Does Planet E, receiving 30% more stellar flux, develop a runaway greenhouse effect? Or does its atmospheric composition prevent that? Does Planet D, cooler and further out, retain water ice at its poles? Can both maintain stable climates despite tidal locking? The answers reshape our understanding of habitability. Not just for this system, but for thousands of similar systems across the galaxy. Red dwarfs are everywhere. If we can understand how planets behave around one quiet red dwarf, we gain insights into countless others. But keystone systems present challenges too. Observing one planet is difficult. Observing two in detail requires twice the telescope time, twice the data analysis, twice the computational modeling. Resources are limited. Every hour spent on TOI-700 is an hour not spent on another target. Scientists must prioritize. Is this system worth the investment? The consensus so far says yes. The combination of proximity, stellar stability, and multiple habitable zone candidates makes TOI-700 a prime target for future observation campaigns. The next major step involves atmospheric characterization. That's where the James Webb Space Telescope enters the picture. JWST, launched in December 2021, has the capability to analyze exoplanet atmospheres in unprecedented detail. It works through transmission spectroscopy. When a planet transits its star, some starlight passes through the planet's atmosphere before reaching us. Different molecules absorb specific wavelengths of light. By analyzing which wavelengths are absorbed, scientists can identify what's in the atmosphere. Water vapor, carbon dioxide, methane, oxygen, ozone. Each leaves a distinct signature. For TOI-700D and E, this technique could reveal whether atmospheres exist at all. If they do, what are they made of? A thick carbon dioxide atmosphere would suggest Venus-like conditions. Water vapor and nitrogen would indicate Earth-like composition. Methane could point to biological processes, though it can also come from geological sources. Oxygen is particularly interesting. In Earth's atmosphere, oxygen is constantly produced by photosynthesis and constantly consumed by geological processes. The only reason we have abundant oxygen is because life keeps replenishing it. Finding oxygen on another world wouldn't prove life exists, but it would demand serious investigation. JWST isn't the only tool. Ground-based telescopes equipped with advanced spectrographs can measure planetary masses through radial velocity. As a planet orbits, it tugs on its star, causing tiny wobbles. By measuring these wobbles, astronomers calculate the planet's mass. Combined with radius measurements from transits, mass reveals density. Density tells you composition. Rocky, icy, gaseous. The 2024 ESPRESSO observations that measured TOI-700D's mass at 2.40 Earth masses came from this technique. More observations will refine that number, reducing uncertainty. Future missions will push capabilities further. The European Space Agency's Ariel mission, planned for launch in 2029, will focus specifically on exoplanet atmospheres. NASA's Habitable Worlds Observatory, still in early planning stages, aims to directly image Earth-like planets and analyze their atmospheres in even greater detail. These missions won't launch for years, but TOI-700 is already on their target lists. Direct imaging presents unique challenges. Planets don't emit much light. They reflect their star's light, but they're billions of times fainter than the stars they orbit. Imagine trying to see a firefly next to a searchlight from 1,000 miles away. That's the scale of the problem. Advanced coronagraphs can block starlight, revealing the faint glow of planets. But it requires extraordinary precision. For TOI-700, direct imaging would show whether clouds exist, how they distribute across the planet, and potentially even surface features if resolution permits. What would we actually see if we could look at TOI-700d directly? That depends entirely on conditions we don't yet know. If the planet has a thick atmosphere with global cloud coverage, it might appear as a featureless white or gray sphere. If clouds are patchy, we might see variations in brightness as the planet rotates. A cloudless world could reveal surface features. Blue oceans would create a distinctive color signature. Red or brown landmasses would contrast against blue water. Ice caps at the poles would shine bright white. Tidal locking complicates this picture. Remember, one hemisphere always faces the star. If the planet has oceans, they might concentrate on the day side where temperatures allow liquid water. The night side could be covered in ice. The terminator region, the boundary between day and night, might be the most temperate zone. Wind patterns would differ dramatically from Earth's. Instead of the complex circulation driven by rotation and differential heating, tidally locked planets develop simpler patterns. Winds blow from the cold night side toward the hot day side at low altitudes, then return at higher altitudes. This creates a permanent storm system centered on the subsolar point, the spot on the planet directly facing the star. Scientists have simulated these conditions. The models show that even with extreme day-night temperature differences, a thick atmosphere can maintain habitable temperatures in the twilight zone. Water could remain liquid in a band around the terminator. Life, if it emerged, might cluster there. Or perhaps life would adapt to the extremes. Organisms on the day side might burrow underground to escape heat and radiation. Night side life could thrive beneath ice sheets, drawing energy from hydrothermal vents like Earth's deep ocean ecosystems. But we're getting ahead of the data. Right now, we don't know if TOI-700d has water. We don't know if it has an atmosphere at all. The planet could be a barren rock, stripped of volatiles early in its history. Or it could be an ocean world with no land. Or something in between. The density measurements suggest a rocky composition, but they allow for various scenarios. A planet with a large iron core would be denser than one with a smaller core. A thin atmosphere adds minimal mass. A thick atmosphere of heavy molecules like carbon dioxide adds more. Temperature calculations offer clues but not certainties. The equilibrium temperature, assuming no atmosphere, would be minus 4.3 degrees Celsius. That's below freezing. But Earth's equilibrium temperature without an atmosphere would be minus 18 degrees Celsius. Our actual average surface temperature is 15 degrees Celsius. The 33-degree difference comes entirely from atmospheric greenhouse warming. If TOI-700d has a similar atmosphere to Earth, its surface temperature could easily be above freezing. If it has a thicker atmosphere, temperatures could be much warmer. If it has little to no atmosphere, the surface stays frozen. The possibility of a runaway greenhouse effect hovers at the edge of plausibility. Venus experienced this. Early in solar system history, Venus likely had oceans. As the sun gradually brightened, Venus received more energy. Water vapor entered the atmosphere. Water vapor is a greenhouse gas. More water vapor meant more warming. More warming meant more evaporation. Eventually, the oceans evaporated completely. Without liquid water to absorb carbon dioxide through weathering and lock it into rocks, CO2 accumulated in the atmosphere. Surface temperatures soared to 465 degrees Celsius. The planet became hell. TOI-700e, receiving 30% more flux than Earth, sits closer to this danger zone. TOI-700d, receiving 12% less flux, has more breathing room. But the margin isn't huge. These are the questions that drive exoplanet science forward. Not just finding planets, but understanding them. Not just knowing they exist, but determining what they're like. Every new data point refines the picture. Every observation narrows the possibilities. The process is slow, methodical, frustrating at times. But it's how science works. You start with unknowns. You gather evidence. You build models. You test predictions. You revise and repeat. TOI-700 has moved from discovery to characterization. The next phase involves detailed atmospheric studies, refined mass measurements, and potentially direct imaging. Each step takes years. Telescope time is competitive. Data analysis is complex. But the potential payoff justifies the effort. If either planet D or E proves habitable, it changes everything. Not just for exoplanet science, but for humanity's place in the cosmos. The James Webb Space Telescope changes the equation. Launched in December 2021, Webb operates in infrared wavelengths, perfect for studying exoplanet atmospheres. Its instruments can detect molecular signatures that Hubble and Spitzer couldn't resolve. For a planet like TOI-700d, Webb represents the best current tool for atmospheric characterization. But there's a challenge. TOI-700d transits a relatively dim star. The signal is faint. Detecting atmospheric features requires extraordinary precision. Webb needs multiple transits to build up enough data. Each observation window must be carefully planned. Telescope time is precious. Thousands of proposals compete for access. Projects are ranked by scientific merit and feasibility. TOI-700d made the cut. Observations are scheduled. Results will take time to analyze. But when they arrive, we'll know things we can only guess at now. Does the planet have an atmosphere? If so, what's it made of? Water vapor, carbon dioxide, methane, oxygen. Oxygen would be particularly significant. On Earth, nearly all atmospheric oxygen comes from photosynthesis. It's a biosignature. Finding oxygen on TOI-700d wouldn't prove life exists there, but it would be compelling evidence worth investigating further. Methane adds another layer. Methane breaks down quickly in UV radiation. Its presence requires constant replenishment. On Earth, both geological processes and biological activity produce methane. Detecting methane alongside oxygen would strengthen the case for biology, though false positives remain possible. scientists will look for combinations of gases. Single detections can mislead. Multiple biosignatures together build a stronger argument. The absence of expected gases can be just as informative. If TOI-700d has an atmosphere but lacks water vapor, that tells us something important about its history. Beyond atmospheric composition, scientists want to understand the planet's climate. Models suggest various possibilities. Some scenarios show a temperate world with moderate temperatures across both hemispheres. Others predict extreme conditions, scorching on one side, frozen on the other. Atmospheric circulation determines which scenario prevails. On a tidally locked planet, heat transport becomes critical. If the atmosphere can't move heat efficiently from day to night, the night side freezes while the day side bakes. If circulation is robust, temperatures moderate. Earth's atmosphere transports heat through wind patterns and ocean currents. Something similar could happen on TOI-700d. Cloud formation matters too. Clouds reflect incoming starlight, cooling the planet. They also trap outgoing infrared radiation, warming it. The balance depends on cloud altitude, thickness, and composition. High thin clouds tend to warm. Low thick clouds tend to cool. On a tidally locked world, clouds might form preferentially on the day side where heating drives convection. This could create a natural thermostat, regulating temperature by reflecting excess light back into space. Computer models explore these dynamics. Teams run simulations with different atmospheric compositions, pressures, and rotation rates. They input the known parameters: stellar flux, orbital period, planetary radius. They vary the unknowns: atmosphere thickness, greenhouse gas concentrations, surface properties. Each simulation produces a different climate outcome. 20 different models were created for TOI-700d early in its study. One depicted an ocean world with a carbon dioxide atmosphere similar to young Mars. Another showed a dry, cloudless planet resembling a barren version of modern Earth. Others fell somewhere between these extremes. Each model is plausible given current constraints. We won't know which is correct until observations provide definitive answers. The ocean world scenario is particularly intriguing. If TOI-700d has global oceans, the implications are profound. Water is essential for life as we understand it. Oceans provide stable environments where complex chemistry can occur over billions of years. On Earth, life likely originated in the oceans. The same could happen elsewhere. Ocean depth would influence habitability. Too shallow, and you limit the available volume for biological processes. Too deep, and pressure at the ocean floor creates exotic ice phases, even at temperatures well above freezing. These high-pressure ices would form a solid layer at depth, potentially isolating the ocean from the rocky mantle below. That isolation could limit nutrient cycling and energy sources. The ideal ocean depth depends on many factors. Scientists estimate that oceans several kilometers deep might offer the best balance. Deep enough for volume and stability, shallow enough to avoid high-pressure ice formation. But this is speculative. We don't have direct measurements of ocean depth on any exoplanet. Surface composition provides another piece of the puzzle. If TOI-700d has continents, it could support weathering cycles similar to Earth's. Rainwater reacts with rocks, dissolving minerals. Rivers carry those minerals to the ocean. Marine organisms use them to build shells. When those organisms die, their remains settle to the seafloor, locking carbon into sediments. Eventually, plate tectonics subduct those sediments back into the mantle. Volcanoes release the carbon as CO2. The cycle continues. This carbonate-silicate cycle regulates Earth's climate over geological time. When temperatures rise, weathering accelerates, removing CO2 from the atmosphere, cooling the planet. When temperatures drop, weathering slows, allowing volcanic CO2 to accumulate, warming the planet. It's a negative feedback loop that maintains stability. Does TOI-700d have plate tectonics? We don't know. Plate tectonics requires specific conditions: a rocky mantle, sufficient internal heat, and a crust that can fracture and move. Earth has these. Venus doesn't, despite being similar in size and composition. The difference might come down to water content. Water lubricates the mantle, making plate tectonics easier. A dry planet might have a stagnant lid, with no recycling of crustal material. Internal heat drives geological activity. Planets generate heat through radioactive decay of elements like uranium, thorium, and potassium. Larger planets retain heat longer. Smaller planets cool faster. TOI-700d, at 1.16 Earth radii and 2.4 Earth masses, should have internal heat comparable to Earth's. That's enough to drive volcanism and potentially plate tectonics, assuming the right conditions. Magnetic fields add another variable. Earth's magnetic field is generated by the motion of molten iron in the outer core. This field extends into space, deflecting charged particles from the solar wind. Without it, our atmosphere would gradually erode. Mars lost its magnetic field early in its history. Its atmosphere thinned. Water evaporated. The planet became the cold, dry desert we see today. Does TOI-700d have a magnetic field? The high bulk density suggests a large iron core, which is promising. But having an iron core isn't enough. The core must be liquid and convecting. That requires sufficient internal heat and a right chemical composition. Earth's core contains lighter elements like sulfur and oxygen mixed with iron. These elements lower the melting point, keeping the outer core liquid. If TOI-700d's core is pure iron, it might be entirely solid, producing no magnetic field. Atmospheric loss through solar wind erosion depends on several factors. Stellar wind intensity, planetary gravity, atmospheric mass, and magnetic field strength all play roles. For TOI-700d, the stellar wind pressure is expected to be similar to Earth's. That's favorable. The planet's gravity, given its mass and radius, is about 1.8 times Earth's. Stronger gravity helps retain atmosphere. If a magnetic field exists, that's another layer of protection. Scientists estimate that an Earth-like atmosphere on TOI-700d could survive for more than 1 billion years, even without a magnetic field. With one, survival extends to billions of years, comparable to Earth's atmospheric age. This longevity is crucial. Life, if it exists, needs time to develop. A planet that loses its atmosphere quickly won't support complex biology. The comparison with TOI-700c is illuminating. Planet C, the sub-Neptune, has retained an extended hydrogen and helium envelope despite receiving more than twice the stellar flux that Planet D receives. If the star's high-energy emissions weren't strong enough to strip C's atmosphere, they're even less likely to affect D. This suggests that D could maintain a secondary atmosphere of heavier molecules like nitrogen, oxygen, and carbon dioxide with relative ease. Time will reveal more. Each new observation refines our understanding. The first Webb observations will focus on atmospheric detection. Do spectral lines show evidence of molecules? If yes, which ones? If no, does that mean no atmosphere exists, or is the atmosphere transparent at the wavelengths observed? Follow-up observations will provide deeper analysis. Multiple transits across different wavelength ranges. Comparisons with climate models. Searches for seasonal variations or weather patterns. Each layer of data brings us closer to knowing what TOI-700d is really like. The discovery process for TOI-700e adds context. TESS observed the system for an additional year after the initial discovery. That extended coverage revealed a fourth planet, smaller and closer to the star than D. TOI-700e is 95% Earth size, orbits every 27.8 days, and sits at the inner edge of the habitable zone. It receives 30% more flux than Earth. Having two potentially habitable planets in one system is extraordinary. Keystone systems like this are rare. They offer unique opportunities for comparative studies. How do two similar planets in the same system develop differently? What factors determine which remains habitable and which doesn't? These questions guide research priorities. The proximity of both planets to the boundaries of the habitable zone makes them test cases. TOI-700e pushes the inner limit. TOI-700d sits more comfortably within the zone but still faces questions about atmospheric retention and climate stability. Together, they bracket the range of conditions where life might emerge. Future missions will build on TESS and Webb's work. Concepts for large space-based telescopes designed specifically for exoplanet imaging are under development. These instruments would block starlight directly, allowing planets to be seen as separate points of light rather than inferred from transits. Direct imaging would enable detailed surface mapping, cloud tracking, and long-term climate monitoring. For now, those capabilities remain years away, but the groundwork is being laid. The search for life elsewhere has always been driven by technology. Each advancement brings new capabilities. New questions become answerable. The James Webb Space Telescope represents the current frontier, but it won't be the last. Already, concepts for next-generation observatories are taking shape. Missions designed to go beyond atmospheric characterization and actually image exoplanets directly. To see them not as transiting shadows but as distinct worlds separated from their stars. These proposed telescopes would use massive star shades or internal coronagraphs to block stellar light. With the star's glare removed, planets become visible as individual points of light. Spectroscopy could then analyze that light directly, revealing atmospheric composition, surface features, and potentially even biosignatures. Cloud patterns could be tracked across days and weeks. Seasonal changes monitored. Long-term climate trends documented. For TOI-700d, direct imaging remains a challenge. The planet is relatively small and close to its star. Current technology can't resolve it. But future instruments, larger and more sensitive, might succeed where current tools cannot. Concepts like the Habitable Worlds Observatory aim to do exactly this. To find and characterize potentially habitable planets around nearby stars. To answer the question that has haunted humanity for millennia. Are we alone? The technical hurdles are immense. Blocking starlight precisely enough to see a planet billions of times fainter requires extraordinary engineering. Maintaining that precision over long observation periods demands stability that pushes the limits of spacecraft design. Yet similar challenges were overcome to build Webb, to launch TESS, to create instruments that can detect molecules in alien atmospheres from 100 light-years away. What would direct imaging reveal about TOI-700d? If the planet has clouds, their distribution would tell us about atmospheric circulation. A tidally locked world might show a permanent cloud deck on the day side, where warm air rises and condenses. The night side could remain clear and cold. Or, if atmospheric winds are strong enough, heat redistribution might create a more uniform appearance. Surface features, if visible, would transform our understanding. Continents and oceans would appear as variations in reflectivity. Vegetation, if present, might produce a distinctive spectral signature called the red edge, where chlorophyll absorbs visible light but reflects near-infrared. Earth's biosphere is detectable from space because of this feature. An alien biosphere using different chemistry might show different patterns, but patterns nonetheless. Time series observations would be particularly revealing. As TOI-700d orbits its star, different hemispheres come into view. If one side is covered in water and the other in land, the reflected light would vary predictably. If weather systems move across the surface, brightness fluctuations would show their passage. These variations encode information about the planet's rotation, climate dynamics, and surface properties. But direct imaging is still years away. In the meantime, transit spectroscopy with Webb will provide the first real data on TOI-700d's atmosphere, if it exists. Those observations are scheduled but not yet complete. When results arrive, they'll either confirm atmospheric molecules or reveal an airless world. Either outcome reshapes what we know. An airless TOI-700d would be disappointing but not surprising. Atmospheric loss is common for planets around red dwarfs, especially if they lack protective magnetic fields. Without an atmosphere, the surface would be exposed to stellar radiation and cosmic rays. Temperature extremes between day and night would be severe. Liquid water couldn't exist. The planet would be geologically dead, frozen on one side and scorched on the other. An atmosphere, even a thin one, changes everything. It suggests geological activity to replenish gases lost to space. It implies a magnetic field or atmospheric mass sufficient to resist erosion. It opens the possibility of climate, weather, and potentially chemistry that could support life. The composition matters enormously. Water vapor would be a strong indicator of habitability. Carbon dioxide could suggest volcanic outgassing or a runaway greenhouse. Methane might hint at biological processes, though abiotic sources exist. The presence of oxygen would be the most provocative finding. On Earth, atmospheric oxygen exists almost entirely because of photosynthetic life. Without biology, oxygen reacts with rocks and disappears. Finding oxygen on TOI-700d would not prove life exists, but it would demand explanation. Could geological processes produce it? Possibly, through photodissociation of water vapor and hydrogen escape. But sustained high oxygen levels are difficult to explain without biology. Even if TOI-700d proves uninhabitable, the system's value remains. Having two potentially habitable planets, D and E, in one system offers comparative insights impossible elsewhere. If one retains an atmosphere and the other doesn't, why? If both have atmospheres but different compositions, what drives the difference? These questions illuminate planetary evolution in ways studying single planets cannot. The broader search for life involves more than individual planets. It requires statistical understanding. How common are habitable zone planets around red dwarfs? What fraction retain atmospheres? What fractions show signs of water or biological activity? TOI-700 contributes one data point to that larger picture. As TESS and other surveys find more systems, patterns will emerge. Those patterns guide mission planning, focusing resources on the most promising targets. Red dwarfs themselves present a paradox. They're the most common stars, comprising 70 to 80% of the galaxy. Their longevity, burning for trillions of years, offers immense timescales for life to develop. Yet their proximity to planets creates challenges. Tidal locking, stellar flares, and intense radiation all threaten habitability. Whether red dwarf planets can support life remains one of the defining questions in astrobiology. TOI-700d sits at the center of that question. Its quiet star reduces radiation risks. Its position in the habitable zone suggests moderate temperatures. Its mass and density indicate rocky composition. But questions remain. Does it have water? Does it have air? Does it have the stability needed for life to emerge and evolve? We're closer to answers than ever before. TESS identified the planet. Spitzer confirmed it. Webb will probe its atmosphere. Future observatories might image its surface. Each step builds on the last, layering knowledge until the full picture emerges. That picture might show a barren rock, interesting but lifeless. Or it might show a world with oceans, weather, and chemistry we've never encountered. The search itself transforms us. Every planet studied expands our understanding of what's possible. Every atmosphere characterized refines our models. Every system explored adds context. TOI-700d isn't just a destination. It's a lens through which we examine the universe's capacity to create and sustain worlds like our own. 101.4 light-years away, a planet orbits a small red star. It's been there for billions of years, long before humans existed, long before Earth knew life. We've only just noticed it, only just begun asking what it might be. The answers will come slowly, piece by piece, observation by observation. But they will come. And when they do, we'll know whether the universe's habit of creating habitable worlds extends to the most common stars in the galaxy. Whether places like TOI-700d are rare exceptions or countless variations on a universal theme. Whether we're looking at one of billions of living worlds or a sterile ball of rock that never stood a chance. Time, data, and patience will tell. The measurements keep getting sharper. The models keep evolving. But some facts remain constant. TOI-700d exists. It's real, rocky, and positioned where water could survive as liquid if conditions align. That's not speculation. That's physics and observation converging into certainty. What we don't know still outweighs what we do. By a wide margin. The planet could be frozen solid despite sitting in the habitable zone. Atmospheric composition determines actual surface conditions, and we haven't detected that atmosphere yet. It might not exist at all. Stellar wind could have stripped it away early in the system's history. Or perhaps it's there, thick and opaque, hiding the surface beneath layers of cloud and gas we haven't yet characterized. The Webb observations will change this. When those results publish, a significant portion of uncertainty disappears. Either spectral lines show molecular absorption or they don't. Either water vapor appears in the data or it's absent. Either carbon dioxide, methane, oxygen show up in the transmission spectrum or the planet transits against its star without leaving chemical fingerprints in the light. That data is coming. Not in decades. In the next few years, possibly sooner. The observation time has been allocated. The instruments are operational. The analysis pipelines are ready. When Webb turns toward TOI-700 and captures multiple transits across different wavelengths, the planet will reveal whether it has managed to hold on to an atmosphere across billions of years orbiting a red dwarf star. If the answer is yes, everything intensifies. Follow-up observations will attempt to determine composition ratios, search for biosignature combinations, model climate patterns based on detected molecules. If the answer is no, the planet becomes a case study in atmospheric loss. Either outcome advances understanding, but the implications differ dramatically. Consider the timeline. Test launched in 2018. The discovery announcement came in January 2020. Spitzer confirmation followed immediately. Mass measurements using espresso arrived in 2024. Webb observations are scheduled for the near future. From detection to atmospheric characterization in less than a decade. That's the pace of modern exoplanet science. Rapid, iterative, building momentum as technology and techniques improve. Compare that to earlier eras. When the first exoplanet around a Sun-like star was confirmed in 1995, scientists could barely measure its mass and orbit. Atmospheric studies seemed impossibly distant. Now, less than 30 years later, we're debating the composition of specific clouds on planets 100 light-years away. The acceleration is remarkable and shows no signs of slowing. TOI-700D benefits from this momentum. It's close enough for detailed study but far enough to remind us how vast space truly is. The light we observe today left that system during the Roaring Twenties. Before television, before computers, before humans knew galaxies existed beyond the Milky Way. That light traveled through space for a century while we developed the technology to detect and analyze it. The planet itself remains unchanged by our attention. It continues orbiting, locked in its 37-day cycle, one face always toward the star, one always away. If it has weather, those patterns persist regardless of our observations. If it has oceans, they move according to gravity and heat, indifferent to human curiosity. The planet exists independent of our understanding. Our knowledge catches up slowly, asymptotically approaching but never quite reaching complete certainty. That's the nature of studying distant worlds. Proxies and inference replace direct experience. We can't send probes, can't land instruments, can't sample the atmosphere directly. Everything comes through light. Photons that left the planet's vicinity, traveled across interstellar space, and arrived at our detectors carrying encoded information about what they encountered. Extracting that information requires extraordinary precision. The signals are faint, the noise substantial, the potential for error constant. Yet the techniques work. Transit spectroscopy reveals atmospheric composition. Radio velocity measurements determine mass. Thermal emission studies map temperature distribution. Each method has been tested, validated, refined through application to hundreds of planets. The results are reliable within stated uncertainties. For TOI-700D, those uncertainties will narrow as observations accumulate. The planet's radius is known to within a few percent. Its mass carries larger error bars but will improve with additional radio velocity data. The atmospheric composition remains completely unknown pending Webb results. Surface conditions are inferred from models but not observed. The presence or absence of water, the extent of geological activity, the existence of a magnetic field, all await future investigation. Yet we know enough to classify this planet as significant. Earth-sized, habitable zone, orbiting a quiet star, part of a multi-planet system with another habitable zone candidate. That combination is rare. Not unique, but uncommon enough to warrant serious attention. Resources are limited. Telescope time is precious. TOI-700D has earned its place on observation lists through the strength of its fundamental characteristics. The system's architecture adds value. For confirmed planets spanning different size classes and orbital distances. Planet B, nearly Earth-sized but too hot. Planet C, a subneptune with a thick envelope. Planet E, Earth-sized and at the inner habitable zone edge. Planet D, slightly larger and more comfortably positioned. Each planet tells part of the system's formation and evolution story. Together, they provide context that single-planet systems cannot. Understanding how these worlds formed requires modeling the protoplanetary disk from which they condensed. Where did volatiles accumulate? How did planetary migration reshape the system? What determined which planets retained atmospheres and which lost them? These questions apply to every planetary system, but having 4 diverse examples in one location makes the answers more accessible. TOI-700 also serves as a laboratory for red dwarf planet studies. These stars are everywhere. Understanding their planetary systems has statistical weight beyond individual discoveries. If planets around quiet red dwarfs can maintain habitable conditions, that expands the potential for life in the galaxy enormously. If they can't, it constrains where we should focus future searches. The answer isn't binary. Some red dwarf planets will be habitable, others won't. The question is what factors separate the two categories. Stellar activity clearly matters. Planetary mass and composition matter. Orbital distance matters. Magnetic field strength, atmospheric composition, geological activity, all contribute. TOI-700D provides one test case. As more red dwarf planets are characterized, patterns will emerge, separating true habitability from optimistic projection. This planet won't be the last habitable zone discovery. TESS continues operating, finding new candidates. Other surveys contribute additional targets. The sample size grows. But TOI-700D holds historical significance as TESS's first Earth-sized habitable zone world. That designation carries weight, marking a milestone in the mission's scientific return. More important than the milestone is what comes next. The follow-up observations, the atmospheric analysis, the comparison with climate models. The slow accumulation of evidence that either confirms habitability potential or rules it out. The process takes years, but it produces results that reshape our understanding of planetary diversity. In the broader context, TOI-700D represents a single data point in humanity's attempt to answer an ancient question. Are we alone? Is Earth unique, or is it one example of a common planetary type? The answer won't come from studying one planet. It requires systematic surveys, detailed characterization of many worlds, and statistical analysis of the results. But each planet studied contributes essential information. Each atmosphere analyzed adds to the database. Each climate model tested against observation refines our predictive capabilities. TOI-700D isn't just about one world 101 light-years away. It's about building the knowledge base necessary to understand all such worlds across the galaxy. That understanding advances through incremental steps. TESS identifies candidates. Ground-based telescopes confirm them and measure masses. Space telescopes probe atmospheres. Each observation answers some questions and raises new ones. The cycle continues, driven by curiosity and enabled by increasingly sophisticated technology. We're living through a unique period in human history. The first time our species has had the capability to study planets beyond the solar system in detail. The first time we can ask whether specific distant worlds might be habitable and receive data-driven answers. Future generations will have more refined instruments, more comprehensive datasets, possibly even ways to image these planets directly. But we're the first to see these worlds emerge from the noise, to calculate their masses and compositions, to attempt atmospheric characterization. TOI-700d will be studied for decades. As instruments improve, as techniques advance, as our understanding deepens. Each new observation layer adds detail, resolving questions that current technology cannot address. Eventually, we'll know what this planet actually looks like. Whether it has air, water, continents, ice. Whether it's a place where life could emerge or a sterile world that never had a chance. That knowledge changes us. Not because one planet determines our cosmic significance, but because each world studied expands our perspective on what's possible. On how planets form and evolve. On where the boundaries of habitability actually lie. On whether Earth-like conditions are common or vanishingly rare. The answer matters. Not just scientifically but philosophically. If habitable worlds are common, the galaxy might teem with life, most of it beyond our current ability to detect. If they are rare, Earth's biosphere could be precious beyond measure, a statistical anomaly in a largely sterile universe. Both possibilities carry profound implications for how we understand our place in existence. TOI-700d won't settle that question alone. But it contributes evidence. And as evidence accumulates across dozens, then hundreds of characterized planets, patterns emerge. Those patterns guide our understanding toward truth, however slowly, however incompletely. For now, the planet orbits its quiet star, possibly harboring an atmosphere, possibly supporting conditions where water remains liquid, possibly hosting processes we've never imagined. Or none of those things. We'll find out. The observations are scheduled. The instruments are ready. The data will arrive, and when it does, one more piece of the cosmic puzzle will click into place. A high school student noticed an error in a stellar catalog. That error, once corrected, revealed a world that might be habitable. The discovery process was messy, human, imperfect. But it worked. And now that world sits in our crosshairs, waiting to reveal what billions of years of planetary evolution have created 101 light-years from home.